Hello everyone. So here we are going to see the example of symmetric and transitive relationship. So a relation R is symmetric if and only if for all AB belongs to A, we have also BA belongs to R. Okay. So if we find a relationship, if we find a ordered pairs like 2, 3, if it belongs to the relation R, okay, then we can say that this is going to be a symmetric if we also find that 3, 2 also belongs to R. Okay, so for all ordered pairs AB, if that belongs to A, sorry, this should be actually R. All right, it's not A, this should be R. Okay, for all ordered pairs AB, if that belongs to R, then we will also have that BA belongs to R. Okay, so then the relationship, then we have another type of relation, transitive relation, but we'll talk about that later. Let's see one example of symmetric relation. So let's see the relation. Here is a set of ordered pairs xy belongs to a Cartesian product of all integer number. Okay, Z is a set of all integer number and a Cartesian product of two integer number set. Now x minus y is even. Okay, so set of all ordered pairs where x minus y equals to even. So let's just find out couple of example. Let's just find out couple of ordered pairs which will belongs to this relation R. Okay, x minus y should be even. So 1 minus okay, so let's see 2 4, okay, 2 6, 2 8, 2 10, then like 3 7. Couple of examples, there could be more other examples too, say like 7 3, 7 5, okay, 7 5, then 7 2, it's not 7 1, okay, like that. So these are all belongs to R, because if you find 2 minus 4 minus 2, that's actually a even number. Okay, so 2 minus 4, it's even number. 2 so 2 minus 6 minus 4 even number, 7 minus 3 4 even number, 7 minus 5 equals to 2 even number. Okay, so these all are part of the relation R. Now pick any one of the number for all ordered pairs. If we find out for all ordered pairs, if we find out the BA also belongs to R, then we can say that this one is symmetric. Now let's pick any of the member here, for example 2 4. If we find out the ordered pairs, the reverse ordered pairs like 4 2, that will also belong to R. Okay, because 4 minus 2 is even. 2 6, 6 2 will also belong to R. 2 8, 8 2, that will also belong to R. Okay, we can say that for every ordered pairs AB, if A minus B is even, okay, if A minus B is even, then B minus A should be also even. And if we can prove that, if we can be sure about that, we know that this is going to be a symmetric relation. Okay, so if x minus y is even, then y minus x is also even, and we can actually prove that this is a symmetric, because for every ordered pairs x y, if x minus y is even, then also y minus x will be even. Okay, so we can that's an example proof. All right, and there could be a many proof technique to prove something, prove some theorem, or prove some proposition. So for example, let's see, we want to prove that for all xy belongs to the integer number belongs to the set of integer number. If x minus y is even, then y minus x will be also even. Now let's consider another integer number m belongs to z. Okay, then just any integer number m belongs to z. So then 2m will be always even because it's divisible by 2. Okay, and now let's x minus y equals to 2m. All right, so then multiply both sides with minus 1, minus x minus y equals to minus 2m, and then we can say that y minus x equals to, okay, so x minus y equals to minus 2m, which means that minus x plus y equals to minus 2m, which is y minus x equals to minus 2m. So if 2m is even, minus 2m is also even. Okay, so it's proof that y minus x is also even. So this relationship for every ordered pairs xy, if x minus y is even, then also y minus x is also even. Okay, so if there is an ordered pair xy, then also there is an ordered pairs yx. Okay, so we can say that that's a symmetric relation. Now we'll talk about the transitive relation. A relation R is transitive if and only if for all ABC belongs to, it's actually R. Okay, for so for any three numbers A, B, C, for all three numbers, pair of all for all tuple of three numbers A, B, C, if it happens that A, B belongs to R and B, C belongs to R, then A and C will also belongs to R. Means if A is related to B and B is related to C, then A will be also related to C. Okay, then we can say that this one is a transitive relation. So let's see one example, one relation R. R is given fixed positive integer number. Okay, K is a given fixed positive integer number, and R is a relation. R is a relation where we have the set of ordered pairs. A, B belongs to all integer number. A, B belongs to all integer number. Okay, and A minus B is divisible by K. So the relation says that a set of all ordered pairs where A, B belongs to integer number and A minus B is divisible by K, and K is given by fixed positive integer. Okay, then can we show that R is a transitive relation? So let's find out. Say let's see K is 5. The K will be given. Okay, it says saying that K is 5. Then find out some members of R. All right, so some members of R will be 5, 10, 10, 5, 10, 15. Okay, then we'll have 15, 20. Okay, then 15, 30, 30, 15, like that. Okay, so these are some example of members. These are some example of members in R. So you can see that for all ordered pairs, we can see that A minus B is divisible by 5. Okay, A minus B is divisible by 5, divisible by K, where K is given. All right, now can we say that this relation is reflexive? If we can find some two ordered pairs like that, if 5, 10 belongs to R and we have 10, 15 belongs to R, can we say that 5, 15 also belongs to R? Okay, so if we can prove that for A, B belongs to R and B, C belongs to R, we can say that for every A, B, C, if we can prove that, then we can say that this one is a transitive relation. Okay, all right, now from here it is going to belongs to R because 5 minus 15, it's minus 10, and minus 10 also divisible by 5. Okay, All right, so here what we can do, so we can prove it like that. So we know that a minus b belongs to R, means a minus b is divisible by k, and b minus c is belongs to R, means b minus c is divisible by k. So if we add these two number, that will be also divisible by k. For example, you can just assume that a minus b is divisible by k, so this is kx, x is any number. Okay, so b minus c is divisible by k. Let's see, b minus c equals to ky. Okay, now if we add them, a plus b, sorry, a minus b, b minus c, all right, that is going to be kx plus y, which is k times x plus y. Okay, which is also divisible by k. So a minus b plus b minus c is also divisible by k. Okay, all right, now what is this one? A minus b plus b minus c, which is a minus c. Okay, so a minus c equals to k times x plus y, which is also divisible by k. All right, so it is proved. Now it is proved actually for any positive integer number k. So we can say that AC belongs to R. Okay, so that means R is a transitive relation, and we use this notation to say that that's the end of our proof. Now anti-symmetric relation means actually this is opposite of symmetric. Okay, so if we have a set A where AB, for all AB, okay, for all AB belongs to A, if we find like ABBA belongs to R, okay, this will only imply that A equals to B. Okay, so if we have some member here, a b belongs to R and ba belongs to R, so this will imply only if a equals to b. Other than that, for any other number, it is going to be false, that if ab belongs to R, then ba will not belongs to R. If they belongs to R, this will be only possible if a equals to b. Okay, so let's see one example. Let's see R is a relation where x, y belongs to R, Cartesian product R, and x is less than or equal to y. Okay, so now x is less than or equal to y. So let's see some number of let's see some member of R. Okay, x is less than or equal to y, so there will be 2 2, 2 3, 2 4, 3 3, 3 4, like that. Okay, so because the first element has to be less than or equal to y. Okay, first element has to be less than or equal to y, second element. So now what about that? So if AB belongs to R, okay, now let's find out BA. So for this one, 2 2, they A and B, they are same, so this one belongs to R. Now if we find out BA also belongs to R, that will only prove that A equals to B. Okay, but other than that, there will not be any other value. For example, BA, like say here we have 2 3, 3 2 is not going to belong to R because 3 is not less than or equal to 2. Okay, so here, from here, 4 3 is not going to belongs to R because 4 is not less than or equal to 3. Okay, so a antisymmetric relation means actually if AB belongs to R, then BA will belongs to R only if A equals to B. Okay, so other than that, BA is not going to belong to R. A equivalence relation means we can say relation equivalence if the relation is reflexive, symmetric, and transitive. Okay, then we can say that R is an equivalence relation. Okay, so A be a set, R be a binary relation on A, Okay, then R is a reflexive symmetric. If R is a reflexive symmetric and transitive, then R is an equivalence relation. Okay.